Hello everyone and welcome to chapter 17. There'll be a bunch of videos from this chapter. It only has 6 sections, but we're going to cover a bunch of material that's not in the book. This video will cover the first 3 sections. Should be pretty straightforward. We're looking at relations and functions. What do they have in common? How are they different? And we'll also learn about what domain and range are. These are concepts that we can immediately apply to things we've already studied, like linear functions, but the rest of this course is pretty much all functions all the time. We will shortly be seeing quadratic functions, exponential functions, trigonometric functions, other functions that we might not know the name of, or maybe they don't even have a special name. We'll be able to determine whether something that we're looking at is a function or not, and we'll be able to work out through a variety of techniques what its domain and range are. So for starters, what is a relation? It's any set of points which connects two variables. And I want to come back to set of points in just a moment, but let's just look at an example first. So here we've got, okay, there's some statues for sale. We've got a graph displaying some information about those 5 statues. Pretty straightforward, I think. What are the variables? The variables are the things that are changing here. That would be the weight of the statues and their cost. Which statue is the heaviest? Okay, pretty clearly from looking at this graph, I think statue E should be the heaviest. Which ones are the most expensive? Again, if we look along the cost axis, statues B and E appear to be the most expensive, and then the least expensive would be statue A. Now, back to a set of points. Those points could be displayed in a graph, as we have here. They could be expressed in a table, as we see up there. Now, I've just kind of pretended that this graph we saw had, like units of 1 along each axis just to generate the 5 coordinates. Obviously, we don't even have units on the graph, so I'm making up these numbers. They're not necessarily representative of the statues in this problem, but whatever. The point is, we could see our set of points as a graph or as a table, or also down below as just a list. We could list out the points. And usually when we do that, we write them out inside of the squiggly brackets, also known as braces. So those guys there. And then you just write the coordinates in those. Now you should already be having some flashbacks to when we studied linear functions, because there we talked about having graphs of the lines. We also talked about having just the points listed out. And I think usually in a table was how we discussed that. In those examples, we could also generate a rule, an equation that described the pattern. We can't really do that here, but that's because this is not a special type of function. This is just a general relation. So don't try to come up with a rule for these. You can see from just the picture, it's going to be quite challenging to do. We'll talk more about rules in a couple of minutes. I wanted us to keep thinking about relations a little bit here. Just 2 other examples of what a relation might look like if it were graphed. So here we have the number of shoppers in a store over time. So we see the number of shoppers increases, and then it might go down, and it might increase again, and so on. Looks like in this case, someone checked the number of shoppers in the store at particular points in time, and then they just connected those with straight lines to generate this graph, which is fair enough. It's unlikely that the number of shoppers would be exactly along these lines. If we looked at, say, like noon, for example, it's unlikely that the number of shoppers would be exactly, what do we want to call that, 33? It might be that the graph decreased in a different way. It might be that it actually continued going up and then had a sharp decrease. We don't really know because they only counted the number of shoppers in the store at 11 and then again at 1. On the right, we have another kind of weird looking graph. This is the cost in, by the way, if you don't know that currency, that's just Swiss francs. It's not important. So we have the cost of some items, I don't even know what it is, compared to their weight. So kind of like the statues again. And what this notation tells me there is that Any of these objects which are in between 0 and half of a kilogram are all going to cost the same amount. They're all going to cost 5 Swiss francs. Any object that's in between half a kilogram and an entire kilogram, they're all going to cost, what is that, 8 Swiss francs. Everything between 1 and 2 kilograms is going to cost 10 Swiss francs. Everything from 2 to 3 is going to cost 11 Swiss francs. You're going to notice that here, for example, if we take a look at x equals 1, it's filled in there, and it's not filled in there. That tells me that when we have exactly 1 kilogram, the cost we're interested in is 8 Swiss francs, not 10. Had this one not been filled in, and that one were filled in, okay, then the cost for 1 kilogram would have been 10 rather than 8. Anyway, I think you're smart enough to figure out how to read a graph like this, and this really isn't where I want to emphasize our time here. So let's move on and talk about domain and range. The domain is going to be the set of possible x values, and often we think of these as the independent variable in situations. Some of you may know the phrase independent variable from like a science setting, or maybe you've seen it in a previous math course, so I include that here. The range, on the other hand, is a set of possible y values, and that would be our dependent variable. So essentially, the items in blue are all, I don't want to say they're interchangeable, but they all basically mean the same thing. These definitions say that they're for relations, but this is absolutely going to still be true in the next section when we talk about functions, because a function is just a special type of relation. So everything that's true for a relation will be true for a function as well. So we'll look at a couple of more graphs, and we'll try to analyze what their domain and ranges are. So in this first one, we have, looks like part of a line. We notice that it's filled in at this endpoint, but it's not filled in at that endpoint. So if we're considering the x values, what are the x values that are allowed? This is an x value of 1, and we've got every x value in between there and this last one, which is 5, but 5's not included. So we could say that the domain is 1 less than or equal to x less than 5. Look, a very professional way to write this answer is here, where we write, again, the squiggly brackets, and then it's x, and then we write this vertical line, which is shorthand for the words such that, and then we just write the inequality. We don't need to do all that, okay? If you just write the inequality for the domain, we're good to go. Similarly for the range, the highest y value is here, that's 3. The lowest y value is down here, that's -2. But again, -2 is not included. So we write -2 less than y less than or equal to 3. No need to use the braces, no need to write the y such that, just give me the inequality. For our second example, this is called a parabola. You may have studied these before. If not, we'll be seeing them very, very soon. Well, looking at the domain here, this seems to go on forever to the left and the right. So that means that the domain is all x values, and we actually have a few different ways that we can write this. So the first way, again, no need to write the x such that, etc. You can just write this here. So that's x, and then we have, that's not a euro symbol, that's kind of like a curvy, I don't know, it's like a C and then a horizontal line through it, or you could think of it as like a weird curvy E. And that just means that x is an element of, and then we have our set of real numbers. If you prefer, you could express that in words by saying all real numbers. In fact, since this course is only dealing with real numbers, you could probably get away with just saying all numbers, but I'm not going to encourage you to get into that habit because in the future, there's more types of numbers out there. We've talked about that briefly in the past, so to say all numbers is technically incorrect. Or you could also write an inequality in this case using positive and negative infinity. If you want to go that route, please be careful. Don't ever write that x is, for example, less than or equal to infinity. It's not. Infinity is not a number, so x cannot be equal to it. So always use uh, just less than when you're dealing with infinities, never less than or equal to. So now for the range, the smallest y value here is -1, but then it seems like it just goes up forever. So we can write, again, a couple different ways here. We could write y is greater than or equal to -1. That's cool. You could also do a slightly more complicated inequality if you want to show that y is in between -1 and positive infinity. Let's just take a look at a few more. So this first one is another parabola. So again, its x values are going to be all real numbers, but this time its y values, the highest y value is 4, so it's got to be everything less than or equal to 4. In the second example, we have, well, I don't know what this thing is called. It's some curvy shape. If we look at the x values, we notice that there's an endpoint right here, but there's an arrow on this end. So the smallest x value is going to be -4, and then it seems to exist for all x values out to the right of that. So x values are -4 to infinity. The y values, we look through here, what is the smallest y value we see? Well, that's -6. And then we're going to interpret this arrow to mean that it just keeps on going up and up and up. With arrows, it can be kind of ambiguous sometimes. Do they mean that a pattern repeats itself, or do they mean that the graph just keeps going on in the general direction that it was previously pointed in? In all of these cases before us, I'm going to go with the latter because I don't see any repeated uh, shapes in the graphs. So anyway, if I had a graph that looked like this, then I would interpret that arrow to mean that it's going to keep going up and down and up and down and up and down. But that's not what we're dealing with in any of these. So, right, the range. So the smallest y value is -6, and then it appears to be every y value above that. And finally, this third one, this is y equals 3 over x. Now, it looks like it doesn't quite connect here at x equals 0, right? And that makes sense because if x were equal to 0, then we'd be dividing by 0 in this function. So actually this has something called a vertical asymptote. We'll be talking about that a lot later on in this chapter. So its domain is going to be every number except for 0. Because it's clearly the graph exists to the left and to the right of that vertical line, just not at 0. And then its range, well, kind of a similar idea here. It looks like we have every negative value and every positive value, but there appears to be a horizontal asymptote at 0 as well. And that makes sense because there's no way that I could take 3 and divide by a number and have this thing equal 0. So in both cases, we can just say the easiest way to write this is that x is not equal to 0. If you insisted, you could write something ridiculous like negative infinity less than x less than 0 and 0 less than x less than infinity. But I mean, please don't do that. That seems like a whole lot of extra work for nothing. Sometimes looking at a graph can be really complicated. So later on, we're going to look at finding the domain and range from the equation of a function if it's given to us. Or by finding the domain and range just by looking at a table or a list of points. That's actually the easiest one of them all. But since I just referred to the equations of functions, let's talk about functions. I hate the book's definition. They say a function is a relation, which is true. A function is a very special type of relation. But they go on to say it's a relation in which no two different ordered pairs have the same first member. I find that to be very confusing. So here's how I would say it. A function is a relation in which, as I've written above, each x value is paired up with exactly one y value. No x value gets paired up with more than one y value. So we see in the example below, either by looking at the list of points or by looking at the graph, that there are 2 points which have a particular x value being matched up with 2 different y values. We see -1, 3 and -1, -2. That means that the relation that we're looking at in this problem is not a function. That's okay. It's still a relation. We can still answer questions about it, like what's its domain and range? What is its domain and range? Well, the domain is just all the possible x values. What are those? Well, it's -1, 2, 3, or 4. What's the range? Well, it's -2, -1, 2, or 3. You don't need to write them out as pairs. I like to write them out from least to greatest, but it's just a list. Like there's no inequalities here because none of the points are connected. And we could get this domain and range either from, again, looking at the list on the left or from looking at the graph on the right. So the first important thing we need to be able to do is tell whether something is a function or not. And if we have a picture, there's a really easy way to do it. We call it the vertical line test. Basically, we look at a picture of the function and we imagine that we were drawing every single possible vertical lines over the graph. And then we're going to look and we're going to see if any one of those lines happens to cross the graph more than once, then the relation is not a function. So down below we have 2 examples. The one on the right clearly is not a function because there are many vertical lines that we could draw that intersect it more than once. There's 2 lines, one at each end, which only intersect the graph once, and that's fine. That doesn't make it a function because there's tons of other ones, and all we need is one other line that touches it at more than one point. So that's not a function. The example on the left clearly is a function because every vertical line that I draw is going to only touch the function once, or, not at all. In both of these cases, we could have vertical lines that don't intersect the graph at all, and we're not even interested in them. We just care about the ones that intersect it somewhere. So how can we tell if something's a function if we don't have its graph? Well, I guess one option would be to grab a calculator and then graph it and just look at it. But if you don't have a calculator handy, or maybe you just think that would take too much time, you can also play a little game I like to call What's Not Allowed. So when we do algebra, what's not allowed? I think there's 2 big things that you should already be aware of that we're never, ever, ever allowed to do. We know we can't divide by 0, and we know we can't take an even root of a negative, so we can't take a square root or a 4th root, etc. There's other stuff that's not allowed, but we haven't studied it yet, so don't worry about it. Here's one we just saw a few moments ago, y equals 3 over x. What's not allowed? Well, we're not allowed to divide by 0, so that tells me that the domain must be x not equal to 0. The range is a little bit more challenging, and we're going to study this more later on in the chapter, but I'll give you the basic idea of it right now. Essentially, we're going to ask ourselves, what happens as x gets closer and closer to 0? We're going to consider that both when x is a positive number, but also when x is a negative number. And then also what happens as x gets super, super big in both the positive and the negative directions. I think the bottom 2 are a little bit easier to think about. As x goes out towards infinity, so x is a super, super big positive number. What happens to the y value? Well, we have y equals 3 divided by a super, super big number. 3 divided by a super big number is basically going to be 0. It's not going to be exactly equal to 0, but it's going to be pretty close. And the bigger that x gets, the closer the y value will be equal to 0. I'm going to put a plus here to indicate that it's actually a positive number that's really, really close to 0. Similarly, as x gets super big in the negative direction, as x goes out towards negative infinity, we still have 3 divided by a super large number. So the y value is basically going to be 0. But in this case, we will have a positive divided by a negative, which is equal to a negative. For the other two cases, when x gets closer to 0, then we have 3 divided by a really, really small number. And that's going to give us a quotient that's really, really big. So as x gets closer to 0 from the right, in other words, when x is still a positive value, but it's really, really small, our y value is going to go off towards infinity. And when x gets closer to 0 from the left, so when x is still a negative number, but it's really, really close to 0, our y value is going to be super big again, but because we'll have a positive divided by a negative, our y value is going to go to negative infinity. And by looking at these, we can see that our y values, our range, excuse me, should be all real numbers except for 0, because it's never going to quite get to 0. And if you compare what I wrote out here to the picture that we saw before, you'll see that it matches up, right? As x gets closer to 0 from the right-hand side, our y values are going up towards positive infinity. As x gets closer to 0 from the left-hand side, our y values are going down towards negative infinity. As x gets super, super big, our y values are basically 0, but they're still positive. And as x gets super, super big negatively, our y values are again basically 0, but they're going to be negative. Let's just do one more. What about this one? What's not allowed? Well, since we're taking a square root, what's inside of it can't be negative. So in other words, 5 plus x must be greater than or equal to 0. Getting x alone, this means that x must be greater than or equal to negative 5. And that will be our domain for this function. When we think about the range, so the y values, I might start off in this case by considering our absolute smallest x value, which is negative 5. When I substitute that into the function, I get a y value of 0. Now, as x gets bigger, then we're taking the square root of bigger and bigger and bigger numbers. Well, what happens when we take the square root of bigger and bigger and bigger numbers? The answers are bigger and bigger and bigger, right? So that tells me that as x goes off to infinity, the y value is also going to go off to infinity. The bigger x gets, the bigger y gets. So what that means for my range is that my y values must be greater than or equal to 0. Again, it's 0 because the smallest possible x value was negative 5, and when we put in negative 5 into the function, we get 0 out as a y value. Here's a graph of that function, and we see, yeah, the x values start here at negative 5 and then continue out to the right forever, and the y values start here at 0 and then continue upwards forever. Sometimes, I won't show you one of these right now, but sometimes we even combine these. So for example, maybe I could have 3 divided by the square root of 5 plus x. Then I need to worry about the square root can't be negative, but also it couldn't equal 0 because then I would be dividing by 0. So you have to really be careful about what's not allowed. Now, that was a lot, and like I said, we're going to really focus on that more later on in the chapter, but it's good to start thinking about it now. The final thing I'll say on the topic of identifying when something's a function or not is that for the most part, any equation that we write down will be a function. There's one glaring exception to that, but let me just write down a few things. If I write down y equals and then, just a whole bunch of stuff with x's, I could have like pi times x squared minus whatever 41.2 divided by x plus the square root of x minus x over, I don't know what I'm doing. Point is, like, this is definitely a function. It's going to be fine. The place where we have a non-function in an equation is anything where we see a plus or minus show up. And plus or minus usually comes along with square roots. You'll notice here I only wrote plus the square root of all that stuff. So this is definitely a function. I could have also written x minus the square root of all that stuff. It'd still be a function. The only thing I couldn't write is plus or minus the square root of all that stuff. If I do that, then I will not have a function anymore. For example, in this case, if I were to set x equal to, say, 9, then my y value would be equal to the plus or minus square root of 9. Y would be equal to plus or minus 3. And then I have a single x value mapping onto two different y values, 3 and negative 3. So that is contradicting the definition of what a function is. So that's not a function. However, if I just write y equals square root of x, we always interpret that to mean the positive square root of x. So in this case, if x is equal to 9, y is only equal to 3. This one is a function. Sometimes the plus or minus can be hidden. For example, if we had y squared plus x squared equals, I don't know, say 16, this is not a function because when we get y alone, we're going to have y squared equals 16 minus x squared. And then we have to take the square root of both sides. But remember, when we introduce the square root into the problem ourselves, we must write the plus or minus. So this would not be a function. And actually, this is a graph of a circle. So here's y equals the square root of x. Clearly a function. Here's y equals negative square root of x. Still a function. I can't type into Desmos the plus or minus symbol. However, I can just graph the positive square root of x and the negative square root of x, and we can consider this to be one single equation. This is no longer a function because it fails the vertical line test. So it's still a relation, but it's not a function. Here's the other example. That is a circle. Again, the plus or minus, they're going to get us the two semicircles, so the positive and the negative half, that would be put together to get the full thing. Okay, we will end there. I know I went a little beyond the scope of this video with thinking about what happens when x gets out to infinity and gets closer to a vertical asymptote. We're not going to worry about that just now, but that is coming later in this chapter. For right now, I just need you to be able to identify, is something a function or not? You should be able to tell by looking at an equation or by looking at the graph, especially by looking at the graph, or by looking at a list of points, whether they're just listed out or written in a table. You should be able to identify the domain and range from a graph for sure. I think you should be able to work out what the domain is, at least, from an equation by just thinking about what's not allowed, although I admit the range is more challenging. We'll get back to that later. And that's pretty much it, all right? And listen, this is stuff we're going to be dealing with repeatedly throughout the rest of this course. Every time we see a new function, one of the questions we will always be asking ourselves is, what is the domain and range of this particular function? So we're going to be thinking about this constantly. In fact, final question. Let's go back to lines, since that's the one function type that we've actually studied so far. If we're not dealing with a horizontal line or a vertical line, since those are special cases, what's the domain and range of every other line? It's all real numbers for both, right? For a horizontal line, what's the domain? All real numbers. What's the range? Just one number, whatever that horizontal line happens to be at. So if it's the line y equals 7, then the range is just, well, literally y equals 7. What about a vertical line? The range would be all real numbers, but the domain would only be one particular x value. And that tells us that vertical lines are the only line that's not even a function. And, they were always kind of the odd line out, if you will, since all the other lines could be written as y equals, and vertical lines cannot be. Anyway, that is the end for now.